Welcome to Algebra 2, Unit 3, Lesson 2, Part 4, the end of factoring for now. So there are a couple more things that we do need to cover that fall under the umbrella of factoring. We will do those in a future unit, so we will come back to it. But for now, this will be the last lesson that we have covering factoring. And again, I can't emphasize enough, this is a critical skill. Being able to factor is something that's going to follow you through whatever the rest of your mathematical career is. So what I want to start this lesson out with is with your groups, working through these two problems. So x squared minus 16 and 4x squared minus 1. I'm sorry that isn't quite like lined up with the box. Sorry about that. But to try to factor that in groups. Now, if you're watching the video from home and you were not in class, then what I'd like you to do is pause the video and see what you can do to think through this on the area model. Obviously, these look different than some of the expressions that we have been factoring. How are they different? And then what would that mean for the area model? Give yourself a chance to really think about it. It's okay if you don't arrive at like a solution or an answer that you're super happy with, but I do want you to take the time to engage what the problem is and try to think through it. Okay, well, hopefully you had a chance to do that. And if you're still staring at a piece of blank paper, that's not what I had in mind. So what you should have is some evidence that you set up an area model, that you tried to do something with it. So hopefully you started with something like this. So the x squared term goes in that upper left-hand corner. We've done enough of these by now. You've practiced enough on Desmos by now to know, okay, the x squared term, if we're going to do something with an x times something with an x, then x times x is going to give us that x squared in that upper left-hand corner. We also know that the constant term goes in the lower right. Now here you might have some questions, okay? Now this is what we want to do. We want to say that's the negative 16 and over here is the negative 1. But I have had students ask questions like, well, is the 16 positive and the negative would be subtracting whatever the x term is or the bx? No, the negative actually does go with whatever the constant is. So that's a negative 16 and negative 1. It's an excellent question to ask, though. And so if you're looking at your work and said, oh, well, I thought that maybe the negative went with the term that I don't see, and you put a positive 16 or a positive 1 in, like that's part of the wrestling with the problem. And that's fine, but you just go ahead and make the correction now in your notes. Now we have this issue of filling in the middle boxes here, or these boxes that are on the diagonal. And normally we would look at the middle term. So if we had, say, ax squared plus bx plus c, we would look at that middle term to see what it was they had to add up to, and we would multiply the a and the c, and we generate our pairs of factors and look for the pair that was going to work. The problem with this one is there is no bx term. It's just not there. So it's like we have ax squared plus c, where c is negative. Now, where we want to go with this is, what would that middle term have to be? Well, in order for that term to drop out, the b value would have to be 0. Because, and it always comes back to that because. Why does this work? Because 0 times x is 0, and once you don't have the 0 in the middle, like once you have the middle term be 0, you don't need to write it anymore, which is why it's not there. And so what we need is for numbers that add up to 0. And so now, because math is consistent and because the model is consistent, we can do what we did before. We can do 1 times negative 16, and we'd be looking at that negative 16 and looking at the factor pairs. So 1 times 16, 2 times 8, and 4 times 4. And we're looking for a pair that add up to 0. Well, since I know this is a negative 16, I know one of those numbers has to be negative, and lo and behold, if I use the 4 and the negative 4, I can get them to add up to 0. And so we could use 4x and negative 4x. And now if you need to write that down, pause the video and go ahead and write that scratchwork down. I need to erase it because I need this space on the left side. There. Okay, so I'm just going to grab my eraser and just kind of clean that up. I'll leave the factor pairs there in case you need to see them. All right, now this is one of the ones where we can just factor the x squared into x times x. It's a little bit more straightforward. Over here, this would be 4, because since x times 4 would give us the 4x. Down in the lower left, it would be negative 4, since negative 4 times x would give us negative 4x. And then as always, you can use your last box as a check. Negative 4 times positive 4 does give you the negative 16. And so this would end up being x minus 4 and x plus 4. And for those of you that did the assignment back when I gave you the multiplying on the area model problems, there were ones that came out like this, and I actually asked you guys a couple questions like, how are these ones different? What do you notice about the answer? And that was looking at this particular kind of problem in the other direction. Doing our scratch work over here on the right, 4 times negative 1 gives me the negative 4. And then we can generate our pairs. So we have 1 times 4 or 2 times 2. And again, if I'm looking for a middle term of 0, then if one of those twos is negative, negative 2 plus 2 would give me the 0. And negative 2 times 2 would give me the negative 4. And so this would be negative 2x and 2x. And then we have the GCF factor. Oh, that'll be fun. Okay, so looking, I'm going to go, whoops. Hang on. Okay, well, I'm okay with that. I am actually going to go in that direction to get the number up here because it's I don't have to deal with the negative that way. So 2 and 4 have a common factor of 2, and x and x squared have a common factor of x. And from here on out, I can just do it with multiplication. So 2x times what would give me 2x? I don't know why I went down there, but I did. 1 times what would give me negative 1? Well, that would be negative 1. And I guess negative 1 times what would give me negative 2x? That would be positive 2x. Could have done that other ways. And so my factors are 2x plus 1 and 2x minus 1. Now, take a moment and just notice what the factors look like. Just look closely at them. Look at like the terms that are in the factors. Look at how the factors are related to the original expression that you are factoring. Look at the pluses and minuses within them. Okay, just want to be observant of what our answers look like. Right, so what this lesson really gets into is a special kind of factoring problem that's called the difference of squares. Okay, and we want to break down this vocabulary because again, the vocabulary is super important, and it does tip you off as to what the problem actually is. So difference of squares, difference means subtraction. When we say to take the difference, okay, what we mean is to subtract. So if I wanted to know, like, let's say you have a younger or older brother or sister, okay, you have a sibling, okay, I have 2 siblings, okay, I have an older brother and I have a younger sister, and somebody wants to know the difference in our ages, what we would do is subtract. So if I'm going to use made up numbers, but let's say I was 15. At the time that I was 15, my younger sister was 11. And so if you wanted to know the difference between our ages, you would subtract, and we would say the difference between my age and my sister's age is 4 years. It's actually like 3 years and like 8 months. Okay. And my brother and I are similar in the other direction. So he's about 4 years older than me. But difference means subtract. Squares refers to something called perfect squares. Okay, so difference of squares refers to something called perfect squares. So in this kind of problem, what we're really thinking of is subtraction of these things called perfect squares. So I'm going to give you some examples of perfect squares. 1 squared is a perfect square. 1 squared is 1, because 1 times 1 is 1, not to get too challenging there. 2 squared is a perfect square, namely 4. Okay, and it goes on. So 3 squared, which is 9, is a perfect square. 4 squared is a perfect square. 5 squared is a perfect square. Now, it generalizes. X squared is considered a perfect square. It is x times x. And also maybe something like this, 16x squared is considered a perfect square because it is the product of 2 perfect squares, namely the 4 squared and the x squared, or you could think of it as 4x times 4x. So when we're talking about the type of problem that is called the difference of squares, what we mean are perfect squares that are subtracted. So for instance, the difference of squares, and I'm going to abbreviate that DOS like I did with axis of symmetry was AOS, difference of squares DOS, could be something like this, x squared minus 9. How do I know that's the difference of squares? Well, it's difference because it is subtracting, and then the two things that are being subtracted are perfect squares. This is x squared, this is 3 squared. But it could also be something like 25x squared minus 36, because this is 5x squared, okay, or 5 squared and x squared, and this is 6 squared, and we are subtracting them. There is no sum of squares. Well, there is a sum of squares, but we don't factor it, okay? At least not at this level at this moment, because we have to introduce a whole other thing before we can even talk about that. But so this is subtracting, and they're subtracting things that are perfect squares. Now, it is in your best interest to have your perfect squares memorized. You should know them from, say, when you did your multiplication tables. So like I said, 6 squared is 36, 7 squared is 49, 8 squared is 64, 9 squared is 81, 10 squared is 100. Beyond that, then it starts to get a little shaky. I think a lot of people remember that 12 squared is 144, but you get into like what's 11 squared, and like we just don't see that one. There's an infinite number of perfect squares. So past about 100, you might have to bust out your calculator and double check. But if you're doing a lot with perfect squares, you'll actually start to memorize some of the other ones because you'll just see them. Okay. But the smaller ones, hopefully we know. Now, these types of problems always factor according to a particular pattern, and here's what the pattern is. So you can do them with the area model, but like these always work a certain way. They always factor into what are called conjugates. So basically, you figure out what was being squared. So if it's x squared, well, what was being squared was just an x. If it's 16, what was being squared? 4. Okay, so you think about what was being squared, and the two factors are going to be conjugates. So this word is going to come up a lot. Conjugates. Conjugates are when you have the same terms in your factors, but one of them has a plus sign and one has a minus sign. Okay, that's what it means to be conjugates. It does not matter which one comes first. I tend to put the plus sign first, but I don't have to. That's just kind of what I tend to do. So these will always, always, always factor into conjugates. So you just think, okay, what's the first thing that was squared? What's the second thing that was squared? And then split them up with a plus and a minus. So here are some examples. Okay, just kind of show you how these problems roll. So all of these factor into two sets of parentheses. Oh, that one is going to require, actually the middle one does too. I'm going to just asterisk that. It's like not the greatest example that I have there. Well, I might go back and do that middle one two different ways. So what we do, we look at that first one and it says x squared minus 25. And so the first thing we want to do is recognize that that is a difference of squares. Okay, that's what it is. I know it is the difference of squares because it is subtraction. And the two things that I am subtracting are perfect squares. So what was the perfect square in the first term? Well, it was x. Try not to overthink that. X squared is x squared. The other perfect square there is the 25. And you think, okay, well, what squared gives me 25? And the answer to that is 5. And then one of them will be a plus and one will be a minus, and you're literally done with the problem. Now, what do I want to do? I'm going to jump down to that third one down on the end there. So looking at the third one, I can tell that I have a difference because it is being subtracted. The problem is that 18 and 8 are actually not perfect squares. So what we should do is look for that GCF. And I notice that 18 and 8 are both even, which means that I can factor out a 2. And then I ask myself, okay, 2 times what gives me 18? That would be 9. And then we have the x squared, and then 2 times what gives me 8? That would be the 4. Okay, so that was the GCF factoring on the perfect square, or on the binomial. So now if I look at what I've got in there, now I have 9, which is a perfect square, and 4, which is a perfect square, and the x squared, which is a perfect square. So now that I've got the 2 out, now I have the difference of squares. Now don't forget that the 2 is there. So I'm going to bring the 2 down. And then I think, okay, what squared gives me 9? That would be 3. What squared gives me x squared? Well, that would be x. What squared gives me 4? That would be 2. And then 1 is a plus and 1 is a minus. I am barely squeezing that in. I'm going to see if I can write it. I think I can write over my picture there. So this is 3x plus 2 and 3x minus 2. Now, the reason I kind of jumped over that middle one is because the middle one also has a GCF, but you might miss it because 4 and 36 are perfect squares. Okay, and so it actually does factor, and I'm toying in my head here with, do I want to just go factor out the perfect square and show you that way, or do I want to show you what happens if you don't get the perfect square out? So what we'll do, we'll maybe do this one 2 ways. So let's go ahead and factor that as the difference of squares. So I know the difference of squares always factors into conjugates. So we're going to have the plus and the minus. And then we need to figure out, okay, well, what squared gave me these expressions? So it was 2 squared that gave us the 4, and x squared that gave us the x squared, and then 6 squared that gave us the 36. Now, here's where we just realize some stuff is going down. So this is not completely factored, and hang with me for a moment when I grab my pointer. The reason I know that it is not perfectly factored is because 2x and 6 have a common factor. 2 and 6 are both even, which means that there is a common factor of 2. So this is not completely factored. I can get a common factor of 2 out. Here's the other issue. I've got another one of these over here that also has a common factor of 2. So watch how this goes. I'm going to take the 2 out, and that will leave me with x plus 3. Because 2 times x will give me the 2x, 2 times 3 would give me the 6. But that also happens over here. All right, so you can also get the 2. And now what we have is 2 times x plus 3 times 2 times x minus 3. And we could multiply the two 2's together to get 4, because multiplication can be done in any order you like. And now I have it completely factored. Now, that's like if you kind of miss the GCF at the beginning, which is easy to do if you're in difference of squares mode and you're like, difference of squares, good, we got this. But there is that common factor in there. Now, what is probably a better way to do that is, we'll come over here, is to notice that there is a common factor first. That 4 is a factor of 36. And so you can actually factor the 4 out. If you have 4x squared, you factor out the 4, you're left with the x squared. If you have 36, you factor out a 4, you'll be left with a 9. And now the x squared minus 9 is the difference of squares. And that will factor into x plus 3, x minus 3. And you'll notice that you do get the same answer, but it's probably easier to get that common factor out first. Most people don't really like to mess around with this. When they get, you just don't want to mess with it, like realizing you have a common factor still in there. So, but you can get there from here. All right. Now, this also works with the area model, okay? And because of the way I structured the lesson this particular year, I don't think we need to go over this in a lot of detail. The way that I had this lesson structured in a previous year, like we needed to go through this, but let's go through this again because math is consistent and the area model works. It's a great model. It's always going to work. Okay. So it works even when you have a formula to go back on. So we would look at this. We would use the 9 times the -1 to get the -9. And we'd look for those factor pairs. And since we know that they need to add up to 0, we know we're going to be dealing with a -3 and a +3. Doing my GCF factoring, I'm going to go in that direction there. 9 and 3 have a common factor of 3. X squared and x have a common factor of x. And now I can do my multiplication the rest of the way. So what times 3x would give me 9x squared? That would have to be 3x. What times 3x gives me 3x? That would be a positive one. I was like, half my eyes were going over the other one over here. 3x times what gives me -3x? And lo and behold, we have those conjugates. Where we could find out, well, what was being squared. Now, it always works out this way. So I have here, like you may also opt for the formulas. So looking at this one, 36 and 49 are both perfect squares. One of them is 6 squared, one is 7 squared, and it is difference because it is subtracting. What squared gives me 36? That's 6. What squared gives me x squared? That's x. They're conjugates, so one's a plus and one's a minus. What squared gives me 49? And that would be 7. Okay, and really, difference of squares problems should be about that fast, okay? You just need to recognize that you're looking at perfect squares, and you really shouldn't have much more to do than that. Now, this would be awful to do with the area model because there are no common factors and because 36 and 49 are huge numbers to multiply. So you'd So we'd have to do like 36 times 49, and we get some huge number that we would then need to factor. I don't think it's going to have a ton of factors, just because like 49 doesn't have a lot of factors. 36 does, though. It'd be kind of bad. Yeah, it would work, but the numbers would be awful. So use the method that works for you. While the right answer is important, it is more important that you see and something demonstrate the concepts at work. Blocked by my face there. Sorry about that. You'd probably rather see that than my face. Is what it is. So yeah, what's really important is that you're using a method that works for you and that you understand how to do these, not just that you're getting the right answer, because there's all kinds of dodgy ways to get the right answer that don't mean that you understand the math. Okay, so if the area model, if you want to stick with the area model, do that. If you want to use the formula, do that. You are not required to show work for difference of squares problems. Okay, you will not be required to show work for them. So classwork, homework, and for funsies work, because math should be fun too, right? So Desmos 7A and 8A are classwork, and 9A and 10A are homework. So we're kind of doubling up, but you've done enough of the Desmos assignments at this point to know how those assignments work, and you know that they're not like long and involved. So we're talking about a grand total of 12 problems between those 4 assignments. If you finish those early, then I want you to mull over this for funsies. Okay, how could you use a graph to figure out the values of x for this equation? So we have 2x squared plus 9x minus 5 equals 0. I want you to think about it. Try some guess and checky stuff. Try a few things on Desmos. Dump some stuff into Desmos. See what you're able to come up with, okay? And we'll tack that onto your assignment just for funsies, because it's fun to think about a solution for a problem, especially when there's nothing at stake. If you can't come up with one, then you might as well just. All right, as always, you know how to get a hold of me if you've got questions, and I will see you next time.